Okay, so let's go ahead and start. Like I said last time, the lecture is going to be short, probably be 25 minutes, something like that. And before I forget, remember I said last time that if you didn't pass in the activity from last time, you could pass it in today. So let me just tell you the tables that I already have. I have table 1, table 5, table 6, table 7, and table 8. So that means before leaving today, make sure table 3. So table 3, I need an activity from you. Table 4. And that's it, because they got 5 other ones. So. Okay, so just make sure if you didn't pass one in last. Oh, you already have. Okay, that's fine. Now it's just table 3. Table 4. Okay, all right, so just remember before you go. Okay, so the main topic for this short lecture is what a register is. And once you know what a register is, you'll have enough information to do lab 5. Lab 5 is not due till a week from tomorrow, so not till Friday of next week. So you still have plenty of time to do it, but you'll be able to do it after this short lecture. Remember, lab 4, that's due tomorrow. And tomorrow, I think midnight is the time tomorrow it's due. How many people have lab 4 done? Oh, okay, more people here. Okay. So yeah, if you don't have lab 4 done, that would be the next thing to do, provided your table is passed in the activity once we're done here. Also, the activity where you drag over an intermediate signal and then show that signal in the timing diagram for lab 4. I'm going to give you more time to do that if you need it, because as we're going to talk about, you need to do that anyway for lab 5. So if you don't show me today for lab 4, you just show me next week for lab 5, and you'll still get full credit. Okay. All right, but let's talk about registers. But first thing, I just want to point out that this is the code that I gave you at the end of last class for D flip-flop. Okay, so again, I may have some syntax errors here. I don't think, if I do, I don't think I have many, but just be careful with that. I mean, you could use this, start with this, and then if you see some syntax errors, figure out what those are. But this is what you need. That code is what you need to model this module and this module, because like I said last time, even though these modules are named register, they're really not registers. Okay, they're really just flip-flops, because these modules are just storing 1 bit. Okay, this module here is storing the validity bit, and this module here is storing the sign bit. So like I talked about last time, this is the new circuitry of lab 5, and then you're going to hook it up to your lab 4 design. So like over here, you have your lab 4 design. And like I mentioned last time, you're not going to need the decoder for lab 5, so the decoder's crossed out. Also, you don't need the neg output, that's going to be crossed out. And also, you don't need the mux. Okay, the mux that goes to AN. That was the one where one of the mux inputs was 4 tick mark B, all 1s. And the other one was 4 tick mark B, 1 1 1 0. So that was the mux controlling whether a display would light or not. Okay, you're not going to need that. Okay, but everything else, lab 4, right? The rest of the circuitry, this hooks up to it. Okay, this here, this T7, that will hook up to your valid output of your validity checker, or whatever you call that output. Okay, the output of your validity checker. And then this will connect to the output of the AND gate, right? The output of the AND gate that has the sign bit of your results. And then this will hook up to the MUX. Okay, the MUX that has the number, the value of your results. Okay, so you see this module here is storing just a single bit, so that's why it can be a flip-flop. And same thing here, this is just storing a single bit. But this module, this is storing 4 bits, right? Because your result, your number, is represented by a 4-bit 2's complement. Okay, so that has to be a register. Registers are just collections of flip-flops, and you need a flip-flop per bit that you're storing. So a register that's storing 4 bits has 4 flip-flops, okay? Because each flip-flop stores one of those bits. So, you know, if you had a 64-bit register, it would have 64 flip-flops, okay? And these are how the flip-flops are connected. It shows all the clocks. You know, I didn't write it here, but anytime you see that, like less than symbol, or that's greater than, that means edge sensitive, which the clock is. So these are all clock inputs here. Okay, and they all get connected together. And then the D inputs all come together and make a 4-bit input to the register. Okay, so like the register is within, or the flip-flops are what is making up the register. So, you know, this is like the high-level register boundary, if you will. So there's this single clock input of the register that connects to all the clocks of the flip-flops. And then there's this 4-bit D input where one of each of the bits goes to one of each of the flip-flop D inputs. And then same thing, or same type of thing with the Q outputs. They all come together and make a 4-bit Q output of the register. Okay, now I didn't show set and reset and enable, but if you had, say, set, which we do for our register, now that 5, well, all the sets would be connected together. And again, we have a set register input. And it'd be the same sort of thing for reset, same sort of thing for enable, or sometimes we call enable enter. Okay. Now, to model a register in System Verilog, it's rather easy once you have your D flip-flop model. Okay. Because in order to model the register, all you have to do is take the same code that you have for the flip-flop and just do a few modifications. Okay, so once you have this D flip-flop working, like, you know, you create the design source for it, and then you simulate it. Once it's simulating good, you can just take the same code, copy it into another design source that you call register, and now just do these few edits. All you have to do to take that flip-flop code and make it into a register code is change your D input to 4 bits instead of 1. Change your Q output, you know, up where you declare them. Change that from a single bit to 4 bits. And then you just got to make, when you reset it, instead of just a single 0, because, you know, flip-flop just a single bit. Well, when it's a register, you just got to set that to 4 zeros. Okay, now I left out, somebody pointed this out in my earlier class. I forgot to put the 4 tick mark B. Okay, but you would just assign Q to the 4 zeros instead of just 1 0, because now you got 4 flip-flops inside the register. Okay, and you know, same sort of thing when you set it, it's going to be 4 1s instead of a single 1. Okay, but that's all you have to do. Once you have the flip-flop module, it's very easy to get the register module. Okay. Now, by the way, you're not going to like it when I tell you this, but By the way, you could have done the same sort of thing with the RCA, right? Remember the ripple carry adder when you made it all full adders, and you did a structural model, right? Well, you could do a structural model for this too. You could have a single flip-flop design source and then have a structural model that connects this all up together that you see here. Okay, but you did that already once. That's kind of like the long way of doing it in Vivado. Okay, and the reason we had you do it the long way was because we were trying to teach you structural modeling. Okay, but you could have, to do your RCA made of all full adder, you could have taken the same approach. You could have just taken your full adder design source and then made the inputs and outputs of that full adder multiple bits. And the software would do this for you. Okay, so since you did it once, we're showing you the shortcut way now, right? We're letting the software, do its thing. Okay. All right. The next thing is the high-level black box diagram for your lab 5. Okay, because again, this is important because the high-level black box diagram, it shows you your main inputs and your main outputs. So for lab 5, you're gonna have the A and B 4-bit inputs just like lab 4, because those are the two numbers you're either adding or subtracting. You need the sub input, right? That tells you whether you're adding or subtracting. Now, over on the output side, there's a slight difference from lab 4, and that's the seg output has 8 bits instead of 7 bits. Okay, the AN still has 4, just like lab 4, but this seg has, an additional bit. And the reason for the additional bit is because this module here, this universal seg, which Dr. Mealy designed and we provide to you. Now, we don't provide the file, we actually provide the text of the code. Okay, so you're going to have to copy and paste that into a file. But if you look here, the output of this module has an 8-bit seg output. And the reason for that extra bit is because Dr. Mealy, when he designed that module, he included the decimal point that's on a 7-segment display. Okay, so you got your 7 segments, and then there's also a decimal point, and that decimal point has its own bits. Okay, so that's the reason for the extra bit. But there's 2 other inputs that you'll have for lab 5. Okay, you'll have a clear, and remember, clear is the same as reset. So, when you write this code, if you want to use clear instead of reset, that's perfectly okay. And enter. And enter is the same as enable. Now I use enter here, but you can use enable. Sometimes people use load. Okay, they're all synonymous. So what we're doing here, big picture wise, what we're doing here is we're adding memory to your lab 4. Okay, that's what these modules are, right? Flip-flops and registers, they're memory. Also, we're replacing the decoder you designed with this module that Dr. Mealy designed, because that module does what's called time multiplexing. And the reason why this module is nice is because the way the 7-segment displays are connected, the hardwire on your basis board, they will only display the same digits at the same time unless you time multiplex. Okay, like for your lab 4, if you had enabled all your displays so they all lit up, they would all show the same number. Okay. But this module that Dr. Mealy has, it allows you to have different digits on the 7-segment displays at the same time. And the way it does that is through time multiplexing, where time multiplexing is, if you're looking at your basis board and you're looking at your 7-segment displays, well, it will put data on the furthest to the right display. Then it just puts data on the next display left to it. And then it just puts data on the display left to that. Then it puts data just on the most left display. And then it goes back and it just keeps cycling. And it does it at such a fast rate that our eyes can't detect that that's happening. We just see a solid 4-digit number. But really, one of them's there, then this one's there, then this one's there, then this one's there. Okay, but again, our eyes can't detect it because it's going so quickly. Okay, so that's what this module is doing. And the reason we give it to you and we don't ask you to design it is because it's not a trivial design. Okay, when you do the copy and paste of the text we give you, take a moment and just kind of look at the code. Now it's done in Verilog. Okay, I mentioned this last time. Dr. Mealy used Verilog instead of System Verilog. So two things to watch out for when you copy and paste that code from the text file. One is make sure when you put it into your file in Vivado that it doesn't wrap around. Okay, in the past, what has happened on occasion is that once somebody pastes it into the file in their Vivado, some of the comments will actually like wrap around. So instead of a comment being on one line, it goes on two lines, and on that second line, it doesn't have the double slashes. So Vivado thinks it's code instead of a comment. Okay, and it causes all kinds of errors. Okay, so watch out for that. And then the other thing to watch out for is, since it's a Verilog file, when you choose the file in Vivado to paste it into, make sure you choose Verilog. And the way you can double check is it should have a .v suffix. If it's System Verilog, it'll have a .s. I don't know if you've noticed that yet, but okay, so keep an eye out for that. That's two common problems that come up. Now, the other peculiar thing with this module that Dr. Mealy designed is that when he assigned the numbers to the multiple bits AN and SEG, he did opposite of what is conventional. Like we've talked about, what's conventional is you number the least significant bit 0 and the most significant bit the higher number. Okay, like what we've been doing. But Dr. Mealy did it the other way. Okay, he numbered the most significant bit 0 and he called the least significant bit a higher number. Well, where that is important to know is when you do the constraints. So that's why on each table, I put this handout that shows that when you do the numbering in the constraint, you got to do it opposite what you did for lab 4. Okay, in lab 4, for AN, you went 0, 1, 2, 3. You got to go the other direction. Okay, because of how Dr. Mealy numbered his bits. And the same thing with SEG. Okay, instead of 0, 1, 2, it's the other one. And also, you'll notice that again, we're using the decimal point, so you have to give the decimal point a name with SEG 0. Okay, if you number the constraints like lab 4, even if you do everything else correct, your displays are just going to show gibberish. Right, you'll just get all kinds of weird type of LEDs lighting up. You won't get your numbers. Okay, let's see, what else is there? Okay, well, I guess we're ready now. And unless there's any questions, I guess we're ready just to kind of step through my recommended order of things for lab 5. Okay, so like I've already pointed out, start with creating your design source, your design source for the flip-flop. Simulate it, make sure that's good. Okay, once your flip-flop's good, go ahead, create your register, which again, you just take the same code as you do for the flip-flop, but you just make these modifications. Sim it, make sure it's good. Okay, once that's good, go ahead and copy and paste Mealy's module. Now, like I said, this is on Canvas. If you go on Canvas, I think it's under lab resources. You'll see there's a text file. I think it's universe underscore SSSeg, something like that. But you'll see because it ends in .txt. Okay, so you take care of that. Now you don't simulate this module because we know it's good. Okay, so you don't have to simulate that. But now you put everything together, right? You do a structural model, connect this all up, and then connect it to where you got to connect it to your lab 4 circuit. And then you need to sim that. Okay, now, really important. And this is why I feel okay giving you more time to do that activity where you have to drag out an intermediate signal and show it on the timing diagram. Because in order to simulate the top level of this lab 5 circuit, you have to do it. Okay, you'll see that when you run the simulation and you look on the timing diagram at these two outputs of Dr. Mealy's module, they're not going to make sense. And they're not supposed to make sense. All right, it's just the way this module works with the time multiplexing. The simulator can't show you what those outputs look like when they're working. So in order to make sure that your structural design is working, you have to look at what's going into Mealy's module, right? Because we know this works. So if what's going into his module is correct, well, you can count on this being correct. So you're going to have to pull out this signal, this signal, this signal, and put it on the timing diagram and run it and make sure the number going in, the sign bit going in, the validity bit going in is correct for the test case that you're looking at. Okay? So, like I said, if you don't show me that activity where you're dragging out intermediate signal onto the timing diagram and running the simulation like Dr. Benson does in that troubleshooting video, if you don't show it to me today for lab 4, as long as you show it to me next week for lab 5, that's fine. You know, I realize after a midterm, a lot of people, you know, just want to go home and sleep. I mean, I was like that. After I took a test, I took a nap. So if you want to go take a nap, I perfectly understand. All right, let's see, what else here? I talked about the constraint. Oh, I didn't talk about this. This is important. The clear and the enter use buttons instead of switches. Okay, you're going to still use switches for the A and B and a switch for the sub, but make sure you're using buttons for clear and enter. On your basis board, you have 5 buttons. Okay, so don't use switches for this, because I'm going to tell the grader that if anyone uses switches instead of buttons for clear and enter, to take off points. Now, I won't have them take off 3.5 points. I mean, if everything else is working, but they'll probably take off like a point. Okay, so make sure you're using the buttons. I just want you to know that, hey, there's buttons and there's this other section of the constraints that has buttons. Okay. So, like I said, lab 5, you're really doing 2 more improvements onto lab 4. 1 is you're adding memory. 2, Mealy's module that's going to allow us to put digits on all the 7 segments at the same time instead of just 1. So if your lab 5 is working, what you should see when it's on the board, and let's say, you know, you start with like 3 + 2 and it shows a result of 5. Well, if lab 5 is working, when you go to do the next test case and you change the switches, the display should stay at the old result 5 until you press the enter button. Okay? So the old data is stored until you hit enter, because it's when you hit enter that Q gets updated with the new D input. Okay, prior to that, if you're not setting or resetting, well, it's just going to store. Okay, so, you know, if you put your design on your board and as you're changing the switches, the display is changing, you know your memory is not working. You know, that's a problem. Okay. The other thing is, when you press the clear button, no matter what's on the display, before you press the clear button, it should display 0 after you press the clear button. Okay, so you'll see, if you go on Canvas, you'll see that the test cases for lab 5 are the same as lab 4, except you also have to show that the memory is working, and you also have to show that clear is working. Okay. Let's see. Oh, let me do a couple more things. Go at least one more. Yeah, another thing I wanted to point out is on this diagram, right here it says, note bus mismatch. What do you suppose that means? What's a bus? You talked about what a bus is. In the digital world, not like what you ride around town. So what's a bus? Number of bits. Yeah, it's just when you have multiple bits, right? Like a 4-bit bus, 10-bit bus, whatever. So what do you think this bus mismatch is referring to? It's pointing to this connection right here. Yeah, exactly. There's a 4-bit output connecting to a 14-bit input, right? This is a 14-bit input to Dr. Mealy's time multiplexer module, but we're only using 4 bits, right? Because we have 4-bit data. Okay, so that's what it's referring to, that there's a mismatch in bits. But how could we make it match?
It's called, like, you just add things together.
Yeah, it's that concatenation, which, yeah, same thing as just joining bits. So yeah, you could, you know, in your code, use braces for concatenation, but you could just take T8, that's the connection group, T8, and add bits. Why would, well, first of all, what bit would we add, a 0 or a 1? Or zeros or ones? Right, zeros, right? Because clearly we don't want to change the value of that 4-bit binary, right? So you would just put zeros in front, right? You wouldn't put ones in front or zeros behind, right? Because that would change the value. Now, I believe, especially with the newer versions of Avado, the older versions were different, but I think with the newer versions of Avado, even if you didn't match this, it would probably still work. But it's a good practice to actually do it, even if you don't have to. Okay, so I advise doing it even if Avado works without doing it. I mean, at the very least, Avado will give you a warning. You know, we'll say some warning to the effect of, you know, bus mismatch to let you know. Oh, speaking of versions of Avado, today we found out, you know, I found out with the help of my ISA from 8 to 11, that version 2022.2, when you simulate, when you do that procedure, you know, that technique that Dr. Benson shows about dragging out the intermediate signal and then rerunning the simulation. Well, if you have version 2022.2, it seems like quite often the simulator will crash when you go to restart it. Now, if you just refresh it, it seems to be fine. But if you go to restart it, a lot of times, at least many people in my morning and many people in my 12 to 3, that was happening, okay? Version 2022.1, it doesn't happen, or at least I haven't seen it happen yet. And I've seen at least a half a dozen or so today, okay? Now, for this class, if you're not able to restart it and you can do the refresh, it's probably okay for this class. But for CP233, you would definitely want that feature where you can restart, because see, if you can restart it before you start it again, you can type in the amount of time that you want that simulation to run. There's a little window with how many nanoseconds, and you can just edit that to whatever nanoseconds you want. And that's really handy in CP233, because in that class, at the end of the quarter, when you're like finalizing your microprocessor, you're running a program that has like 4,000 instructions. So your timing diagram is humongous. And a lot of times you just want to look at a small portion of it. So if you restart and then put in the time frame you want, you know, just the time interval you want, that's better than running the whole thing, like searching for whatever you're looking for. Okay, but for this class, we don't run anything that long, so I mean, it's not that big of a deal. But if you have the time, what I would recommend is that if you have the 0.2 version, I would uninstall and install the 2022.1. Okay. I wish I had known at the beginning of quarter when I told you then, but like I said, I just found out this morning. So change my summer canvas and put that in. All right, so let's see. Is there anything yeah, this is important. Okay, another thing that's different when you have a sequential circuit, right? When you have a combination circuit, in your sim file, when you have a sequential circuit, meaning you're going to have a clock, you have to create a clock in your sim file. So in your sim file for both the flip-flop, the register, and the overall, all 3 of them, you're going to need this code that I have up here. And this code goes between the UUT line, you know, the unit under test line, and where you start to test cases. So, you know, here's your UUT, here's where you start to test cases. This code was right in between the 2. And it can always block. And always block, as the name implies, always happens. Okay, it just cycles. And inside that always block, we have this block equal 1. So that's going to start the clock at a value of 1. And it's going to keep it 1 for 5 nanoseconds. The number, the number sign indicates that the number is nanoseconds. Okay, you might have noticed when you do test cases, you do number sign 10, test case, number sign 10, test case. That's to separate the test cases by 10 nanoseconds. Okay, so this code is going to keep the clock on for 5 nanoseconds, then it's going to go to 0 for 5 nanoseconds. I'm not making this very straight, but that's just one. So it's going to be 1 for 5 nanoseconds, then 0 for 5 nanoseconds, and it just repeats. So 1 for 5, 0 for 5, and so on. So that's how it's generating the clock, which is a periodic square wave. Okay, now, if this square wave is a 1 for 5 nanoseconds, and it's a 0 for 5 nanoseconds, what's the period? What time is the period? Right, right. As I'm sure you saw, probably somewhere. Right, the time it takes a waveform to repeat, we call the period. And then how do you get frequency from period? Right. So if you have 1 over now, it's a nano, 10 to the left. Very good. All right, 3 in a row. I think that's the, I can't remember the last time I had 3 sections, and each section got that because usually someone says 10 to the minus 6. They get confused with micrometer, but they're doing that right. So, anyone know what that is in frequency? The reciprocal and nanosecond. 10 times 10 to the minus 1. 100 megahertz. The reason we use that 100 megahertz in the simulation is because that's the frequency of the clock on the basis board. Okay, the basis board is running at 100 megahertz. Okay. The other thing with the clock is in the constraints file, right at the very top of the constraints file, there's 3 lines that deal with the clock. And you just have to uncomment those 3 lines, and it will take what you name clock and connect it to the clock on the basis board. Okay, so that's an additional thing you have to do in the thing of the CPE133 that I have on that handout. Okay, so top of the hour here. I think I said everything I wanted to say. So, like I said, I think there's only one thing more that needs to give me get put from last time. So it's up to you. What do you want to say? Work on that 4, or work on that 5, or what else you have, or yeah, but this time.